Today, we're going to uncover the absolutely wild 200-year-old story behind the most advanced technology on Earth. And believe me, it's a journey that starts not with silicon, but with steam, smoke, and good old-fashioned steel.
So let's just start with a number, 60 picometers.
Now, to give you some scale here, a single silicon atom is about 200 picometers wide. So we are talking about a level of accuracy that is literally smaller than one of the fundamental building blocks of the thing you're trying to build. And this isn't just for some lab experiment. This is the kind of precision needed every single day to build the microchips that power our entire world.
So it begs the question, right? How on earth did humanity learn to build machines that can operate with that kind of impossible atomic scale precision? Well, the answer is a lot older and way more mechanical than you probably think.
Okay, let's start by looking at what is quite possibly the single most complex machine ever built by human hands, the EUV lithography scanner. And honestly, calling it a modern marvel doesn't even begin to do it justice.
These incredible machines, built by a company called ASML, have to solve physics problems that just sound like science fiction. I mean, the special light they use to etch chips gets absorbed by air, so the entire machine has to operate in a near-perfect vacuum. And get this, to eliminate any possibility of friction, critical parts don't actually touch anything. They levitate on powerful magnetic fields. All of this is happening while a stage holding the silicon wafer zips around, positioning itself with that mind-bending atomic-level precision.
But here's the kicker. The real origin story for how we achieved all this, it doesn't start in a pristine, clean room in Silicon Valley. No, it starts in a loud, smoke-filled workshop during the Industrial Revolution with a brilliant mechanic and a whole lot of steam.
To really get this, we've got to jump in our mental time machine and go all the way back to the late 1700s, into the world of a guy named Henry Maudslay. He was a genius who basically taught metal how to be perfect.
See, back in his day, manufacturing had this huge problem. Every single screw was filed down by hand, which meant they all had these wobbly, inconsistent threads they called drunken threads. Every screw was its own unique little piece of art that only fit its own custom-made nut. Now just imagine trying to build or even repair a complex steam engine when no two parts are the same. It was absolute chaos, and it was holding back the entire Industrial Revolution.
So Maudslay comes along, and his solution is just brilliant. First, he built his machine on a heavy, rigid iron bed, not a flimsy wooden frame to absorb vibrations. Then, he invented something called the slide rest, which held the cutting tool perfectly steady, completely removing the unsteadiness of the human hand. And finally, he used a super precise lead screw to guide that tool at a mathematically perfect rate. For the very first time, the skill was being transferred from the craftsman into the machine itself. And this created an incredibly powerful feedback loop, kind of like a mechanical version of Moore's Law. His new precise lathe could create a more perfect screw. That screw could then be used to build a new, even more precise lathe, which in turn could make an even more perfect screw. Each generation of machine was literally building its own more perfect successor. This was the birth of iterative improvement in manufacturing.
But you know, one perfect machine in a single workshop isn't enough to change the world. You need a system. You need a universal language that everyone can use. And that brings us to Maudslay's star pupil, a man named Joseph Whitworth.
Okay, so Whitworth realized that before you can measure anything accurately, you need a perfectly flat surface to measure from. But how do you make something perfectly flat if you don't already have a flat reference? It's a real chicken and egg problem. His solution was pure genius. He took 3 metal plates and just ground them against each other in pairs. Any little high spot on one plate would grind down a spot on the other. And by rotating through all 3 combinations, the only possible shape they could all eventually settle into was a perfect mathematical plane. He had created a datum, a true north for flatness. Once he had that basis for flatness, he could standardize everything else. And so he created the world's first standard for screw threads, the British Standard Whitworth. And just like that, a bolt made in one city could perfectly fit a nut made in another. He basically took his mentor's precision and turned it into an industrial language that everyone could finally speak.
And here is where this whole system proved its awesome power. During the Crimean War, the British military desperately needed 90 gunboat engines, and they needed them yesterday. Before Whitworth, this would have been totally impossible. But now, workshops all across the country could build different parts, and they could be confident they would all fit together perfectly. They built an entire fleet in just 90 days. Standardization had become a massive strategic advantage. For the next 100 years or so, the entire world ran on this incredible mechanical precision. But to build what was coming next, well, we were going to need a whole new kind of ruler, one that wasn't made of metal.
The big shift really started in the late 19th century. Mechanical precision got so good that scientists started using it to build amazing new instruments. A physicist named Henry Maudslay used the world's most perfect screws to build these things called ruling engines. Their only job was to etch tens of thousands of perfectly parallel lines onto a piece of glass. This created something called diffraction grating, a tool that could split light into a spectrum, turning a mechanical marvel into a new way to study physics.
And then the true revolution arrived in the late 1970s with this machine, the GCA 4800 stepper. Now, instead of cutting metal, this thing projected microscopic circuit patterns onto silicon wafers, stepping across the surface to build up a chip, layer by tiny layer.
And this is where the fundamental shift happened. See, Maudslay's lathe was always limited by the physical perfection of its screw, a piece of metal that could wear down or have tiny flaws. But the stepper? It used a laser interferometer. Its ruler was no longer a piece of hardware. It was the unchangeable, absolutely perfect, universal wavelength of light itself.
So this brings us full circle, all the way back to that EUV scanner we started with. Because if you look really closely, you can see the DNA of those 19th century pioneers running right through the heart of this 21st century machine.
I mean, the numbers here are just staggering. Back in 1855, Whitworth's best machine could measure down to about 25,000 nanometers. Today's ASML stage gets down to 0.06 nanometers. That's over 400,000 times more precise. The technology is completely different. We went from metal screws to magnetic levitation, but the core idea, a mechanism guided by a feedback loop, is the exact same principle from the 1800s.
You know what's so wild? The engineers building these modern machines are still battling the exact same enemies as Maudslay and Whitworth. Vibration. Maudslay used a heavy iron bed. ASML uses an actively floating raft. Positioning errors. Maudslay perfected the screw. ASML uses lasers and magnetic levitation. Heat warping the parts. They had to deal with it, and so do the modern machines, just with way, way more advanced cooling. The problems are the same, only the scale has become atomic.
So what this all really boils down to is that the digital revolution wasn't just born in a lab coat in Silicon Valley. Its foundations were literally forged in the smoke and fire of the Industrial Revolution. This whole new world is built on a bedrock of physical, mechanical perfection that was established 2 centuries ago.
When you look at it this way, you see it's all one single, unbroken story. It's a 200-year-long quest to hunt down and eliminate every possible source of error, to move from the unsteadiness of the human hand to the absolute deterministic perfection of a machine.
So the big takeaway is this. The next time you pick up your smartphone, just remember the iron, the steam, and the mechanical genius that's hiding deep inside it. This whole digital world we live in rests on a physical foundation that was laid down a very, very long time ago. Which kind of makes you wonder, right? What other ancient technologies are quietly powering our world, hiding in plain sight?